Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm here to talk about force. Is it real? In one of my previous videos titled Magnetic Field, What Is It? Bob Hicks made a comment. He stated, and this is literally what he put in as a comment. He says, I watch videos and read articles whenever I find them, always hoping for an explanation of force. Where does it originate? Does it have physical or material properties? He says, I don't expect an answer, but renaming the strong nuclear force the G2 gravity force does not seem to tell us what it is. And he's got is in capital letters, and he's right. The name itself does not tell what it is. I did answer back, and this is a direct answer. G2 gravity is caused by the G2 particle, which comes from level 2 atoms. Those are subatomic atoms. These are smaller atoms than the atoms on our periodic table. There's whole other discussion about why would I think they're subatomic atoms? But anyway, we move on. The G1 and the G2 particles come from all the stars in the universe and generate a G1 field and a G2 field. Generally, the G2 field, a random flow of particles. These particles will organize into G1 and G2 force field around all objects. I tried to explain this, I think, over a series of many different videos, but I thought Bob's question was valid and other people may have the same question, so we're going to talk about it. But we're going to start first by talking about, is force real? If something is real, it must exist in nature. Does force exist in nature? No. I'm sorry, I don't mean to yell at you. That's a big no, so I made it loud. If it did, you could go somewhere in the universe and find some force. For example, you could take a shovel and a bucket, go in your backyard and start digging around until you found some force. Put it in the bucket, take it into your laboratory, and test it. Or you could go to the ocean or the lake or the atmosphere or outer space and gather something, look for force, gather it up, and take it into the lab and analyze it. Can't do that. Why? Because force does not exist in nature. Force is not real. What force is a mathematical construct. Force is equal to mass times acceleration. To get a value of force, you have to multiply two numbers together. Excuse me. Nature can't do that. A particle might know its mass, but it doesn't. It might know its speed or acceleration, but it doesn't. And even if it did know its mass and acceleration, it doesn't know how to multiply. Nature doesn't know anything about force. Force ends up being a mathematical term as a vector with magnitude and direction. Well, then why do we do it? You ask, but equations are useful, even if they're not real. An inscription above the stage in Royce Hall at UCLA states, education is learning to use the tools that mankind finds useful. Engineers and scientists use equations. They're tools of the trade. We find them useful. That does not mean they represent something real. There are other terms that are mathematical. Momentum, mass times velocity. It's not real. Can't find it in nature. Force is not real. energy is force times distance. If force is not real, clearly energy isn't real either. E equals mc squared is a mathematical construct that is not real, but it might be useful when you're comparing the amount of energy of one interaction, one interaction with another. So what is real? In my book, Gravity is Not Free, I start with one basic assumption. By the way, the first issue of my book was printed but not released. What I say in the book is that the universe is made up of objects that move. That's my basic assumption. And then I go on to define objects and I define motion. And without going into, I actually make a list of things that I think are objects, that are real. But one category is that what we detect by our senses. We detect the earth, moon, stars. We detect water. We detect atmosphere. I can feel it as I wave my hand. We can also detect what is real with instruments. A simple example is a microscope and a telescope. We can't see some of these things without the aid of these instruments. But when we do, we can say these things are real. I define motion as the change of an object's position over given a period of time. Going into a lot of that detail is a whole other subject, but that's what I claim is real. Now back to Bob's question about force. Where does force originate? We humans assume that when an object moves, there was a force that caused it. We use the term all the time. Even Newton said that. He said, I call it a force because that's a common understanding. But Newton, being the scientist that he was, he gets down to the particle level and assumes that when a particle moves, it moved because another particle hit it. And he has this equation. Now, actually, he was trying to decide how to determine the value of mass when he did this. But he ends up with this equation where object 1 has mass 1 and is accelerating at value a1. And the object that it is object 2, which has mass 2, and it has its acceleration as a2. And there's only acceleration at the point of interaction, or during that short period of time when it changes velocity or changes direction. So he starts with that, but one of his problems was gravity. Gravity was a problem. He says, I don't know what gravity is. He doesn't know what the other object is. He may see object 1 move. I can see it has acceleration, but I don't know what this is. I don't know what this is at all. I don't know what the mass is. I don't know what the acceleration is. There's no way for me to deal with this term. So what does he do? He takes this term, or this term, it doesn't matter which, and he abstracts it. He says, I'm going to call it a force, and I'm going to say that force is equal to the mass of the object that I see moving and times the acceleration of that object. Force ends up not as mass times acceleration. Force ends up as a term that has an amplitude, a magnitude, and a direction. In general, it's a vector. Magnitude and direction. And he did that so he could define and ultimately develop. He used this equation and 2 others to develop this equation. And he abstracts the whole idea of what gravity is because he doesn't know this. And he actually is the inventor of the term force. But it's not real. It's an abstraction, a mathematical construct. Bob's second question, does force have physical properties? Some might say that force equals mass times an acceleration, that force has mass and acceleration, but if it's an abstraction, it isn't, as I just said. It has a magnitude and direction. It's a vector, and force is in newtons. You know, it doesn't have physical properties. Now, the particle model suggests that the G1 particle has mass and speed. When this particle hits an atom, that atom moves. That's the interaction. The G1 and G2 particles have physical properties. The G1 or G2 force field is an abstract term that I use to represent an organized stream of G1 or G2 particles that can cause an object to move. So now let me just define some terms. The G1 particle field. Stars release G1 particles, that is, G1 replaces the electron, the photon, and the graviton. And yes, I'm saying they all, they come from the stars. As the stars go through their combustion, burning up, and or nuclear reactions. It has been estimated that there are 70 sextillion stars in the observable universe. That's that number. That's 22 zeros after the 7. The G1 particle comes at us from all directions, from all those stars. And this is the G1 particle field. Some of them are organized, some of them are not. Some of them are low intensity, some of them are high intensity. But this random flow, generally speaking, this mishmash of flow of particles is the G1 particle field. The G2 particle field comes from subatomic atoms, specifically the orbital of the subatomic atoms. By the way, subatomic atoms are much smaller than our atoms in our periodic table. Because they're smaller, the G2 particle has a speed that is higher than the G1. G1 particle has a speed at or about speed c as it orbits in a normal atom, but the G2 particle as a subatomic or orbital must faster or it can't orbit. Okay, got the same statements. There are 70 sextillion stars in the observable universe. The G2 particle comes at us from all directions. And this is the G2 particle field. Can't tell you much about how G2 particle fields are organized or not organized. We don't have enough information. There's no data. Nobody talks about it. This is G2 particle is unique to the particle model. Now G2 gravity, this is the slide I showed in when I explained two gravities. And what the picture shows is that there are G1 particles coming to the Earth from all directions, three-dimensionally, but I'm showing two opposing streams. This has 1,000 coming in, this has 1,000 coming in. As these 1,000 move through, they pass through. 990 of them pass through. 10 of them hit an atom in the Earth and scatter, or they get trapped. Remember the interactions. The atoms can pass through, they can hit or scatter, or they can get trapped. What I'm saying here, these are fictitious numbers, that 10 of them hit the Earth and push the Earth, causing 990 to be moving up in this direction while there's 1,000 moving down. So there are 10 more G1 particles pushing you down than there are pushing you up. And that is the G1 force field. So even though I call this a force field, I don't draw all this other stuff. I just draw the force field. I'm really representing the difference between how many are pushing up or pushing down. Keep in mind, The particles are still there. They didn't 990 particles didn't disappear, and 990 particles here didn't disappear. They're there trying to push you up or push you down. G2 gravity is the same. You have G2 particles coming at you at this from all directions. I'm using the same fictitious numbers. You have 10 more G2 particles pushing down than are pushing up. This is the G2 force field. Conclusion: force is not real. Mathematical equations do not represent something real. Scientists don't tell you that. They talk about it and talk about it, and you get to thinking, boy, this is real. What? And so Bob has a valid question. What is it? If it's real, what is it? Well, it's not. The G1 field or the G2 field is the random flow of G1 and G2 particles that come from the stars. The G1 force field is developed around objects as the G1 particle passes through and interacts with the object. That's the force field. And the G2 force field is developed the same around all objects. There is a G1 and G2 force field around the Earth. The G1 force field is Newtonian gravity. The G2 force field is what causes the blue sky, because as light comes from the sun, it hits the atmosphere and it refracts because of the G2 force field around the Earth, and the blue bends the most and comes into our atmosphere, paints all the particles in our atmosphere with the color blue, and therefore we see this scattered blue light off of the particles in the atmosphere, and we call that blue sky. There's a G1 and G2 force field around all objects, including the Earth. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.